thanks for the introduction, David. I really appreciate it. I'm a field CTO here at Cornelis Networks. Originally was part of Intel, but many years ago, sort of spun out and have been developing technologies, new products on our own. And there's some exciting news to share today, as well as some sort of sneak peek at some results. So happy to be here. So for those of you that aren't really familiar with Cornelis, I'm going to start with a quick couple of overview slides before we get into the details. So Cornelis sells complete end-to-end networking solutions focused on AI and HPC. This includes host software with a highly optimized OFI software stack, management software, SuperNICs, edge and direct-to-class switches, cables, and gateways. And our primary focus at Cornelis is on application performance at scale. We support a wide range of topologies at scale from a single rack all the way up to 250,000 nodes. We have market-leading latency and message rates, and for multi-tenant environments, we offer hardware-assisted partitioning features to create dynamic virtual fabrics. We have some multiple new advanced routing and congestion management technologies to ensure consistently fast performance. And get into some details later on once we get through this overview. And of course, our solutions, we've been around for a while now, are proven. They've been deployed globally by a wide variety of enterprise and government customers. And we do know that we're only a part of the overall system being deployed when we're deployed at a customer site, albeit we're a pretty critical one to ensure maximum application performance. We have a very strong commitment to a rich ecosystem of technology partners. Due to limited space, I'm only showing a subset of the partners, so don't take this as the only set of people. But of course, I'm going to get my little laser pointer going here. Of course, we support Intel CPUs. That's been our bread and butter for years. We also support AMD CPUs, AMD and NVIDIA GPUs, custom ASICs. We're fully qualified by all the leading OEMs. We work with a lot of the major storage vendors in market, and we have a rich set of compatibility on the software stack side. And my next slide will get into a little more detail on the software side. And then as we're looking into the future, we're really looking at what are the interconnects of the future. So we're part of Ultra Ethernet Consortium, we're part of UA Link. And on the sort of customer application side, we have a wide variety of customers and a wide variety of commercial and open source applications. We work closely with a range of leading ISVs to provide market-leading performance and a seamless end-user experience. So we're out there, we have lots of strong partnerships, and our customers are excited about, again, the news I'm going to be sharing here. So on the software stack, we moved our focus to open fabrics interfaces, libfabric several years ago. We saw there was a fundamental mismatch between application semantics and the semantics of OFA verbs. And that caused system-wide inefficiencies and degraded application performance. So those that aren't familiar with libfabric, it was designed to very closely match application semantics, and it provides a much better set of abstractions to interface closely with a wide variety of hardware, networking hardware. Through libfabric and a native OFI provider, we delivered very, very tight integration of our software and hardware solutions. So software on the host and the hardware goes in the host. And one key metric that this process achieved is that we've reduced the number of CPU cycles required to send a message by 80%. And when you reduce the CPU load when you're sending messages, obviously nothing but goodness in terms of latency and message rate performance, as you'll see. And together with advanced hardware architectures, we do really have industry-leading performance metrics. As you can see, OFI itself has wide support across many different MPI libraries, APIs, and application frameworks, giving us broad application compatibility. And one thing that's very important to Cornelis is this little thing here. We are big proponents of open source. And one of the decisions that was made early on is everything is going to be open source. Our drivers are upstream to mainline kernel. And what this does is allow our customers to take advantage of our advanced networking capabilities without having to install potentially disruptive third-party kernel modules. So we go from the standard Linux kernel development process, and it's solid, it's good to use. So it's a key advantage for Cornelis. Now, again, the big news I want to share is that we're bringing our CN5000 solutions to market over the next couple of months. And the first element in our solution is our CN5000 SuperNIC. It's a 400 gigabit per second, low profile PCI Express Gen 5 device. We have single and dual port variants with single ports on the QSFP. The dual port looks very similar, but it's on the QSFP DD. We carry both links out of a single connector. We support air cooling, and we have two different variants of liquid cooling models to provide full flexibility to our customers and our OEM partners. And the power consumption on the Super NIC is around 20 watts. The next element in the CN5000 solution is our edge switch. It's a 48 port, 1U rack mount, non-blocking 400 gig switch. We have redundant hot plug power supplies and fan trays. And the switches can be flexibly deployed across the data center, supporting lots of different kinds of topologies. We have fat tree, we have HyperX, we have different kinds of flies like dragonflies and megaflies. And our switches are managed through OpenBMC, so easy integration into the data center. We offer both air and liquid cooled versions. On the liquid cooled side, we use quick connect ripless connectors, so very easy to deploy in a liquid cooled environment. And then the sort of the final major hardware element in a CN5000 is our direct-to-class switch. So it's based on a 17U rack mount modular chassis. It delivers up to 576 400 gigabit per second ports. Now, the way the director works, it includes both edge and spine switch modules connected in a non-blocking fat tree. So having the leaf and spine co-located provides lots of advantages. You no longer have optical cabling between the leaf and spine layers. You reduce all that complexity, all the power, all the cost. And we actually have a unique capability in the direct-to-class is that we actually don't have a backplane. So we actually avoid any kind of cabling required within a director itself. So the way that works is our leaf switches, you can kind of see it here in the diagram. I hope it comes across in the Zoom, but they're mounted vertically. So these are 48 port leaf switches. And then the spine switches are accessed from the other side of the director, and they mount horizontally. And on the back of each of these modules, the leaf modules and the spine modules, are high-density, high-performance, high-speed connectors. And what happens is when I plug in this leaf switch on the left, there's a connector on the back that happens to mate with a connector directly on the spine module itself. So I just plug these cards in from different directions, and they mate naturally and create the topology without any cabling, very high efficiency, very low power consumption, all in a single unit, and it's scalable in place. So lots of advantages of Director. A lot of our customers deploy in sort of middle of row, end of row, and just do optical cabling down to the endpoints. Also, of course, with the edge switches, support copper cabling to the Director class, if that makes sense for your topology. Lots of flexibility in how these different switches can be deployed within your environment. And of course, the Director is a high availability solution, fully redundant. All the modules are hot pluggable, and of course, both air and liquid cooled variants. So next, going to get into a little bit of the architecture, that's sort of hardware components. Now we're getting into sort of the details of how does data flow through an OmniPath or Cornelis network. So this is a CN5000 Super NIC architecture that I've mentioned already, but application performance really is our North Star. So it's what we're mainly, I can't even say it. It's what maniacally focused on. And so one of the keys to maximizing performance is to have a very flexible architecture and a tightly integrated software stack that can take advantage of your flexibility. As I said before, LibFabric is our primary software framework, and our provider uses the right combination of our hardware and firmware capabilities to optimize the performance of each application. So as an example, each process running on the nodes in MPI rank is assigned one or more of these dedicated parallel pipelines that are embedded within the hardware. And excuse me, if you're sending small messages, the process on the host actually directly accesses these pipelines. Very thin, very optimized software path. This is a form of programmed I/O where the CPU is directly talking to our card. Through programmed I/O, we achieve sub-microsecond one-hop MPI latency and 40 to 100% higher message rate when compared with NDR. When we have large messages to transfer, we have send SDMA engines or SDMA engines. There's a cost to setting up the software to use these SendDMA engines. So they're typically used when you have large messages, and the break-even point's around 32 kilobytes or so to use SDMA to get best performance. Now on the receive side, we have programmable packet processing engines, which have sort of deep pipelines of flexible matching rules, allow us to use advanced upper-level protocols and provide advanced matching capabilities. Regardless if you used PIO or a SendDMA on the transmit side, data is always placed directly into host memory when it is received, either into an application buffer if you're doing a rendezvous, or into a ring buffer if you're doing eager messaging and for processing. Sort of a final sort of uniqueness on our architecture is that we had to use opaque addressing. We don't use virtual memory addresses to communicate from process to process. So instead, like RDMA uses virtual addresses from each of our processes' memory spaces. So what we do instead is that we have these opaque identifiers. So the local soft Windows card will set up these receive pipelines with rules in terms of if you see a certain identifier, that relates to this physical memory space where my process lives. So the far end just sends using these opaque identifiers, which allows them to send without having to exchange that memory information in first. The only memory information mapping is done on the host side, the receiver side. That allows us to get some very interesting architectural improvements and just make transfers more efficient overall in the architecture. All right, so the next sort of OmniPath characteristic is that we use something called LIDs. These are local identifiers, and they're the addresses used within an OmniPath network. They're similar to MAC addresses in Ethernet networks. In the CN5000, we're introducing a new concept called a hierarchical lid, or HLID. And so the CN5000 can use these 24-bit HLIDs to support a wide range of network scales and network topologies. Depending on the topology of a network, the HLID is broken down into different sets of subfields. The intent, the sizes of all of these fields is fully programmable by the Fabric Manager. So we're able to support a wide variety of topologies today and other topologies into the future, all hardware assisted. So the way these fields work is almost like coordinates to find a SuperNIC within the infrastructure. If you're in a factory, the first field will be, well, which pod am I in? The next two fields will tell you which switch you're on. And the last field may tell you, well, which port of that switch am I connected to? And if we're in a Dragonfly, the first field may be the virtual router group. The next will be the switch within that virtual router group. And the final one, again, will be the endpoint within the switch. Same thing with 3D HyperX. Regardless of topology, what Fabric Manager does is once it's calculated routes, as it's programming all the switches in the fabric, it's putting in rules to traverse between sets of coordinates. So I have a little example here. On a certain switch, if I need to move from virtual routing group 7 to the node located at 612, that's a virtual group 6, switch 1, and endpoint 2, the next hop the switch will be programmed with is a set of egress ports that will get you to that destination. As you'll see next couple of slides, we have advanced routing capabilities that allow us to choose from a set of ports. So in this case, it's you want to get to a certain virtual group, use this set of ports. What that allows us to do is have very efficient route tables. You don't need to have routes to every destination, routes that get you on the way to the right destination. And that allows us to get on a single cluster, single subnet, up to about 250,000 nodes. This also scales down, of course, down to single rack, single row deployments. Just it's very, very flexible and can be configured by the operator to be optimal for very different use cases. Okay, so I talked about routing. There's two different routing techniques we're going to talk about. The first is something we call static dispersive routing, or SDR. So what I have here is a very simple diagram trying to show endpoints and layers of switches. So on the left, we have an endpoint. On the right-hand side, we have an endpoint. We have a leaf switch at each side that the endpoint's connected to. And then we have a typical fat tree sort of layers of switching in the middle. This is a very wide network just to show off the kinds of capabilities we have with SDR. So SDR is designed for when the application semantics require in-order delivery. So when the application says, hey, I need this stuff to arrive in order, libfabric, our provider, marks each of those packets saying, hey, these should be routed using the SDR algorithm. So here I'm showing 4 parallel flows. Each of them is marked with SDR. And the way this works is there's a hash calculator at each switch hop that's based on a subset of the important header fields within each packet. The sort of, I'll call them mandatory fields, the ones that always make sense, are destination lid, hash based on where you're going, then hash on a special field we call entropy. So entropy is a software controlled field, and it identifies which packets are related and must arrive in the order you send them. So it's not a hash of like a port number or a queue pair, it's simply a hash of a software programmable field. And as long as packets are marked with the same entropy fields and have the same destination, they'll of course go down the same path and arrive in the correct order. We have other optional fields that the operator can use to further expand the hash source of hash data. So we have the service channel, which is like a combination of our virtual lane and traffic class. We have different transport modes. We have partition keys. You can even hash on the source lid. The idea is that all these parallel flows will be distributed by SDR across all the different potential paths all the way across the switch. So, of course, the first thing that happens in any of these routing decisions is how do you get to different destinations? Each switch has a very large set of next hops to get to that final destination. The other routing algorithm that we have on the CN5000 is called fine-grained adaptive routing, or FGAR. This is the exact same network as we had on the previous slide, same switches, same next hops programmed at each switch. In contrasting with SDR, FGAR is designed for when application semantics allow out-of-order delivery. So you can take advantage of multipath, you can take advantage of spraying on a per packet basis across the entire network. So in this case, the application said, yes, please, I'd love to see maximum performance, even in congested state. I'm okay with out-of-order delivery. So all those packets will be marked for FGAR. And what happens here is that we take a look at what are the next set of hops and what are the current optimum set of next hops. And the way we determine optimum set of next hops is, I'm just showing it in one direction here, but all the switches are continually sharing congestion state and telemetry with all of its neighbors. So all those switches in this layer are aware of the congestive state of all of the switches in this layer, and so forth. And so when I'm looking to route a packet out one of my egress ports that are defined, I'm looking at my local congestive state, and I'm looking at what are the next hops congestive states. So I'm sort of looking ahead to see, well, what is this packet going to see in the next switch along this path? And in this case, showing an example at the top here, we were routing along this blue line as we were distributing the packets. But now I said, oh, there's some congestion, that information is shared with its neighbor. And now the next time a packet comes, this optimum set of next hops will be different, and one of those will be chosen. So as congestive state changes in the network, this telemetry is updated to all the neighbors, and the right decision is made. This allows us to packet spray as much as we want across the network, because we already know application semantics allow the out-of-order delivery. So a very advanced capability. And the very interesting thing is you have two processes that are communicating using the same hardware pipelines, those contexts from earlier. They can have a mix of packets marked for SDR for in-order delivery and FGAR for spraying packets across the network. So maybe you're ready to send clear to send for a rendezvous, we'll use SDR, and the bulk data would then use FGAR. So fully flexible, programmable pipelines, and a libfabric provider uses the right ones at the right time to ensure application semantics are met correctly. Okay, and now I wanted to share a sneak peek at some early performance data. Now, this is out-of-box data. We've not done any software tuning, any stack tuning, so take it with a grain of salt. But this is on Emerald wrappers using Intel Micro benchmarks. And what we show here is our one-hop full-stack MPI latency. And you can see that for 8-byte messages, we're below a microsecond. So very, very fast latency performance. And even when we go up to 16 kilobyte messages, again, pretty significant advantage over NDR. But the details for the tests are below. I'm not going to go through them. I'll leave that as an exercise for you guys later when you get a copy of the slides. And the other set of results I wanted to share is on message rate. And again, what we have here is unidirectional message rate at the top, bidirectional at the bottom. This is before scaling, scaling and software tuning. This is before we've tried to adjust performance. This is literally out-of-box performance. On the left here, I know it's too small to read, but it's 1 process per node all the way up to 48 processes per node on 1 socket. On the bottom, we also go to 2 sockets, 96 processes total. And what we're showing here is a very significant message rate advantage for 8-byte messages. In this sort of small number of processes per node, to 2 times higher than NDR. So what we're showing really is the results of that tight integration between our architecture, our focus on performance in the architecture, and our software architecture working together to always deliver market-leading application performance. So we're very, very excited to share these kinds of results with the community. And then finally, have a quick look at our solution roadmap. We're shipping CN 5000 solutions to our partners and customers over the next couple of months, and we're already seeing very strong demand, as you can imagine, from our existing user base, as well as new customers for both AI and HPC applications. Next year, we're introducing the 800 gigabits per second CN 6000, and this uses the same sort of hardware pipelines we've proven out in the CN 5000. We're actually adding native Rocky V2 Ethernet support for customers that want mixed fabric types. And then in the following year, we have a CN 7000 coming out. This actually combines three different protocols. We have OmniPath, we have Ethernet Rocky V2, as well as Ultra Ethernet support, also having a full set of different switches, the edge, the director, supporting all these different protocols. All right, so that's all I have for today. Looks like I'm kind of right on time. So any questions?
Yeah, perfect. Very interesting. Thanks for covering the waterfront there. It's exciting to hear what new is coming. I don't see any questions in the Q&A. I had one though. I mean, your the initial design of OmniPath was very much HPC and optimizing for MPI and checkpointing and things. And now your goal is AI as well.
Yep.
Are you actually making changes to the network, or do you think OmniPath kind of works fine for AI as well without massive changes?
There, obviously, AI and HPC are different sides of the same coin, is what I'll call them. HPC, very latency message rate focused. There's a lot of parts of AI that also have similar constraints. What we've done by moving to these advanced routing algorithms to allowing very large scale in a single sort of flat subnet architecture is we're moving to also support AI requirements. So we're able to, at very large scale, ensure that we don't hit congested hotspots. And that could be a problem with existing AI networks, as an example. As you get to scale, it's very hard to ensure the network's not getting in the way. Because we visit advanced technologies, we're looking at switch hop ahead to see where congestion is, be able to route around these bottlenecks and ensure consistent performance even as we're scaling. So it's not that we're not doing HPC. It's HPC is still a strong focus for us, but it just so happens that AI applications have similar requirements, a couple of additional flavors that actually benefit the HPC community as well.
Interesting. All right, there's a couple that came into our Q&A system. Also, if somebody is a panelist, I don't believe they get to use the Q&A system, so just unmute or put your digital hand up. So, all right, so the first one, are there any protocols or their parts offloaded to adapter hardware?
Yeah, I'll flip back to the picture I had. Maybe I didn't go through that detail enough here. So yeah, so there's all this dotted line here is hardware accelerated capabilities. So these are hardware resources. And again, there's parallel sets of these to support multiple processes, multiple threads, however you want to distribute it. Maybe it's multiple customers in a virtualized node. And they are dedicated hardware resources to accelerate all these different methods we have to achieve high message rate, low latency, or high throughput. And again, on the receive side, these are all hardware accelerated matching engines that allow us to do some very, very interesting things. We'll share more of that in the future. It allows us to get very, very good performance to delivering data directly into application memory. So yes, the evolution of Cornelis has been to add more and more accelerating offload capabilities into the endpoint, the SuperNIC. That is a sort of one example of moving along that path.
Cool, thanks. All right, second question. Will the Ethernet and Ultra Ethernet stacks have much more overhead on performance? I.e., will there be benefit to using mixes of OmniPath and Ultra Ethernet together?
I would say what Ethernet has going for it is compatibility and existing infrastructure within data centers. What Ultra Ethernet has going for it is they're trying to put more of a focus on HPC and AI while building upon an Ethernet foundation. What we have an advantage for is traditional HPC applications, scientific modeling, simulations, things like that, where it's all about latency and message rate. So if you think of what the CN 7000 is going to be, it's going to allow you to access the best of all worlds. If you need low message rate and low latency, high message rate, it will do the right thing in that circumstance. If you want to have compatibility with existing Ethernet endpoints, I won't call them legacy. I mean, there's a lot of performance there. That's again, it's the right solution for you. If you have Ultra Ethernet because you're adopting that technology, again, it will do the right thing and you have that capability available to you as well. So I would say it's not, you don't have to choose what you want. We'll deliver the right kind of capabilities for our software layers to again optimize for the different application requirements.
Yeah, to kind of follow on with that, are you actually exposing 3 stacks to the user, or are you doing that under the covers?
Details to follow,
Okay.
but I will say from an end user perspective, it will be very easy to use.
Okay. Let's see. Next question. You mentioned lower latencies than NDR. Where do you attribute this? Also, does bandwidth look at larger message sizes?
Here we
Or
here's the link.
how does bandwidth look at larger message sizes?
So, well, we'll start with a latency question. So there's different reasons why our latency is better, but it really comes down to two. One is that we have this programmed I/O capability where if you need to send a message out, the fastest software path is to talk directly to the card. And we have the lowest number of CPU cycles, lowest number of lines of code to get that message to the card. That allows us on a single CPU core to send as many messages as you can. Small message performance is really bound by the number of operations you can run on the CPU. It's not idle, it's not memory bound, it's really not network bound. It's how quickly can you poke at the NIC to say, hey, or super NIC to say, hey, we need to send a message. The other part of it is our software stack is very optimized, highly tuned. The path to get from application request down to actually hardware sending a packet is very, very small. So those two together allow us to hit more messages per second, allow us to use less latency in the CPU and across our network switches, which are also latency optimized to get the lowest latency performance. Now, the bandwidth one, I didn't quite understand the question. Can you repeat it?
Yeah. Also, how does bandwidth look at larger message sizes?
Oh, we're not sharing those results yet. We'll be sharing more and more over the next couple of months. So stay tuned is probably the right answer there.
Okay. Let's see. I think we have time for one last question here. And do you offload any collectives to hardware? Do you support hierarchical collectives or non-blocking ones?
Let me just that is something we're targeting in the CN 7000 timeframe. Due to time, I didn't go through all the lines here, but yeah, we have Fabric and app offloads planned for the CN 7000 timeframe.
Okay. Great. One last chance for anybody who's a panelist if you want to unmute and ask a question, since you can't use our Q&A system.
So I saw a lot of newer switches coming into the market. They have more latency, and seeing his presentation, I'm really excited to leverage those low latencies, especially with the newer generation, the InfiniBand or whatever the switch is. Like they do have a lot of high latencies, but this is great. Thanks.
Yeah, I'll quickly add it back. Thanks, Ahmed. I really appreciate it. One of the design principles for the switch ASIC teams is get the lowest latency possible, and that has always been a driving design factor. And that's why our sort of cut through latency across that switch is so low. So the latency of results I showed, right, obviously as a switch hop, you gotta get it across a switch very quickly. So if you have a latency bound application or message rate bound application, um, we have the highest performance solution in market. And it also happens to have better power efficiency. The direct provides very interesting cost and operational cost optimizations, as well as complexity reduction. So together, Cornelis has a very strong solution for HPC. And as we move into AI, it just so happens that we also have a very strong solution for AI. So we're very, very excited about this year. Bringing new product to market is always fun, and looking forward to talking more to the community over the next couple of months as we fully launch the product.
Well, good luck for you.
Thank you.
Thanks, Matt.